Let's get started. Today we are going to continue our our lecture series on web security. We're going to start with web attacks. So last time we kind of got a little bit of an intro of like the same origin policy and how what our attacker models were concerned with. Today we're going to look at a bunch of different kinds of web attacks. We're going to start with client-side attacks, but then we're going to also look at some server-side attacks that we didn't talk about last time too much. Okay, so let's get started. I want to kind of first just point out that there's lots of different class of bugs on the web that you'll have to deal with if you're building web applications. Hopefully your framework of choice handles many of these, but if it doesn't, then I would say you should totally get a better framework. Because like dealing with these manually is actually super duper hard, and you're likely to screw it up. So this is the OWASP top 10, which is kind of the list of vulnerabilities that industry is keeping track of based on what people are disclosing in the real world. What we're going to talk about today is we're going to continue our discussion about CSRF, and then we're going to talk about injection attacks and cross-site scripting. And next time we're going to look at the last one, which is using components with kind of known vulnerabilities or kind of buggy components or untrusted components. Okay, so let's get started with CSRF. Now, to set the context, we want to look at the classic way that we authenticate web apps, right? So I have my browser. When my browser talks to, oh, you still can't hear me. Okay, I thought I bumped it up. Is this better? How's this? If you can't, can you hear me better now? Great. Okay. It might be partly on some of your ends too, because I'm totally maxing out right now. Okay, so we have our browser. We have on the right-hand side the bank that we talked to. Well, when you log in, typically what happens is you send a post request to like /login, let's say, with a particular username and password. The bank actually checks that username and password. If you provide it a legit username and password, usually there's a little bit of back and forth because ideally you'll be using two-factor auth, but we're going to assume that's a separate thing. And then what they're going to do is respond back with a 200, like, hey, this is a good login, and here is a cookie. So we're going to send a set cookie response or a response header that has the name of the thing and then some token that says that you're actually authenticated, right? So then like anytime you perform a request, like let's say get accounts, which would list say whichever accounts you have, you send a cookie, then the bank knows where to fetch the accounts from which part of the database, reply back with the right response. And similarly, if you were to say transfer funds, you'd include the cookie in that request. The bank again looks it up, validates the cookie, and then performs the transfer, assuming the funds and everything else is all well and good. Okay, so CSRF comes into play because in this scenario we have the user, they're logged in, and then somewhere either in a separate tab or you just never like logged out, these cookies are stored by your browser. And then when you visit, say, the attacker.com website, the attacker can just send a post request to bank.com, and the bank happily sends the bank.com cookies when it's making this request, right? So this is just how cookies work, and it's a little bit unfortunate, but this is exactly what happens. So how does the attack come into play? Well, we're gonna look at get and post requests to see the two styles of attacks, right? So we'd ideally not be worried about CSRF because at least semantically get requests say like, hey, please give me the resource that's there, and it shouldn't perform any side effects. But post requests, on the other hand, they do perform side requests, and they're actually more dangerous, and the thing that we're really worried about when we deal with CSRF attacks because they can cause server-side changes. Okay, so if I was the attacker, the thing that I would do as the attacker is get you to a page where I have a form. This is, just a normal HTML form that has an action that will be sent to bank.com/transfer, right? Like we saw in the previous slide, that the post request is how we transfer funds. Then we're going to have a hidden field, because we could just have a hidden, like this whole thing will actually be hidden, that will contain the victim source and well, really just the destination, because we're logged in as the user. So we just need to supply who the recipient of this money is and how much money we want to send, and then we just have a separate part of the script that just automatically sends that submits this form, right? So the nice bit is that the same origin policy like actually helps us here. We can't, as the attacker, see the result of a post request because this is a cross-origin request. So we can't inspect the HTTP response. The bad news is if this actually succeeded, so if we actually made a side effect server side, we transferred your monies to the attacker, right? So let's look briefly on what this actually looks like if we were to, say, draw out the network request between attacker.com bank and my browser. Right. So how does this work? Like we were saying before, the first thing that you might do or one of the steps that we have to do is we would say authenticate with the bank. So we make some request to the bank. Then the bank gives us a 200 OK with the cookie. At a later point, we are tricked to click on an attacker link. So what we're going to do is, say, in a separate tab or even within the same tab, but even a separate iframe, we perform a get request to the attacker's page. So let's say it would just be get, news. And the attacker responds back with, absolutely, I'm going to show you all the best news that you can ever get. Right? So they reply back with a 200 OK and an HTML page that contains the form that we saw in the previous slide, right? So essentially what's going on is the attacker is actually running in your browser. Now, what does this page do when it actually loads in your browser? Well, it performs a request, right? That's what the form does. This request is sent to the bank. It sends all your bank cookies. And if the bank only looks at cookies to see whether or not this is an OK request, it will respond back with 200 OK. And, as the attacker, I'm super duper rich now. Right. So this is how the attack works. Before we move on, so I think like we've seen this kind of a few times by now, but I think it's worth stopping here to take any questions that you may have. Can I get some thumbs up or thumbs down on this being clear or not clear? Okay, great. So these are post requests, right? And we're expecting post requests to be side affecting, but we can similarly perform a CSRF attacks with GET. So there might be a website that will actually perform side effects with GET requests, and then as the attacker, all I need to really do is say inject an image that sends a GET request to bank.com with transfer whatever, and this GET request, if again is only handled by looking at the cookie, will be able to do the same thing that we did, which is essentially transfer your funds, even though the attacker again can't look at the response. Great. So we have a question. So the requests to the banks are post, and the ones to the attacker are get. Yeah. So in this particular case, we were looking at the post-based attack. So here, this would actually be a post to /transfer. But the attacker could perform any kind of request, really, both get and post. In this case, a post attack is something that if the website was like reasonably designed, it would be the only thing that they'd like allow you to do when you're performing this kind of side affecting operation. Whereas for gets, you'd only return like here's your accounts or something like that. But we do have websites that actually do side affecting things with gets. So you really like if you're building a web app, want to avoid this because it's semantically tricky to to web servers, to web browsers. But also, it's just like adding an additional thing to worry about when you're having to say audit your code, right? Like if I know that the only side affecting parts of my web app are post um, requests, then I can just look at those specific controllers and kind of ignore at least the gets for these classes of attacks. Okay, so we looked at CSRF when we're actually logged in, but there's different classes of CSRF attacks. One other is called a login CSRF. So, for example, if you're not actually logged in, right? Like in this case, the attacker assumed that you were logged in, and that's how they were able to perform side affecting operations on your behalf. But they can still do damage even if you're not logged in. In particular, one thing they can do is they can log in to, say, PayPal.com as the attacker. Then when you visit PayPal.com, you're actually already logged in. Because this PayPal, say, form didn't properly handle requests, so it just happily lets anybody log in, right? So like I can just send a request to the PayPal server and I'm gonna, as the evil browser, send a request to PayPal, and this is /login, and this logs me in as the attacker, right? And then I somehow convince you with a phishing email or something like that to then, go to PayPal and start adding a bank account. And if you didn't pay attention that you were kind of logged out of your own account and logged in as my attacker account, you might add your bank account to my PayPal account, and I can get access to this kind of sensitive information this particular way. Another way that has been demonstrated in a nice paper from 2008 is a login CSRF example on Google and Yahoo. So the basic idea is, again, we are the victim browser. We're tricked to visit attacker.com. The attacker essentially just has another form request that they're shipping as a web page. This page, when it gets to our browser, starts executing. It performs a post request to log in. The google.com server happily logs in. So now in your browser, as the attacker, I'm logged in. And then you might just be browsing the web as usual, performing all kinds of Google searches. And one thing I can do is anytime you perform those, right, like these cookies are actually sent to the Google servers, but I, as the attacker, can separately log in from my own machine and look at your browsing history or search history. All right, so this class of attacks is different from the other ones that assumes you're logged in and instead logs you in as the attacker, and they can learn information this particular way. So does Google.com have mechanisms to see where the post requests originate from, or is that too hard? Yeah, so we'll see how to deal with both of these classes of attacks, or the classic techniques for dealing with both, and we're going to get to that in 2 slides. The thing that I wanted to highlight, which I think you're also kind of bringing up in your question, which is that cookie-based authentication alone is not enough to tell the server who is actually performing this request. Like, is it actually from a legitimate user, or is it potentially the attacker? Yeah, so banks definitely time out, but they do all kinds of other crazy things. So banks will log you out to partly avoid these kinds of attacks. They also do way more than cookies. So we'll talk about like what they actually do and what banks really do even more on top of the defenses that we're going to talk about. Before we do that, though, I want to basically just point out that this is not just about cookies. So cookies is the thing that we really care about. But whenever you're building a web app or web server, you need to, on the server side, know who you're talking to, who the request is coming from, right? If you don't, all kinds of other attacks are possible. So, for example, there have been attacks where you visit some attacker page, And what this attacker page does, it's really clever. It's called drive-by farming. It just has a bunch of these image sources. So it's basically trying to load images. In this case, it's trying to load images from 192.168.0.1. And it's this particular like path here too, which is image linksys. And then if it registers an error handler, which is basically, the thing that will get triggered if this particular request actually failed. Right. So what is this attacker trying to do? Well, they're basically trying to scan your local network. So these IP addresses are not public IP addresses; they're local NAT addresses, and we'll talk about what this actually is in the networking lecture. But basically, these are internal to like your home network, and what they can do is basically try to figure out like, hey, what is the IP address of your Linksys router, right? And the way they know how to do this is, well, Linksys the router has a web server running on the little device. And that web server responds to HTTP requests. And one of the things that it might respond to when your browser goes to 192.168.0.1 is a whole page that has, say, the Linksys logo, right? So basically, I can identify what router you have and on what the IP of that router is by just getting you to visit my page that has these kinds of images that essentially are just used to send network requests. Right. So this is actually pretty frightening, especially because these routers have crappy passwords. So as the attacker, I can figure out what that IP address is, log in like half the time, and then mess with your router, which basically messes with everything else. Okay, so this is one example. The other example is one that we talked about before, which is your native applications also have web servers. So they're running on your machine. So for example, Zoom has a web server that's running on, again, one of these internal IP addresses that responds to requests from the Zoom JavaScript code running in your browser to basically make it easy for you to like get the app running and set up the conference call. Right. So like one of the things that this let you do, that this let attackers do, because this server running on your machine wasn't properly written, it was buggy, it would let somebody on the network, when you visit their attacker.com website, to access your camera if you're I think connected with on some call or something like that. I forget the exact details, but the basic idea is they somehow got access to your webcam. I forget the exact attack assumptions. Okay, so again, this is actually maybe even scarier than implementing a web server that you run on your own machines, because now I have a web server that I'm running to that I implemented to run on your machines, and that how to deal with that is tricky. Okay, so before we talk about defenses, the thing again I want to stress is that the thing that these things have in common is that the server that can't tell who's actually making the request. Like, is it their own code running in your browser, or is it the attacker? Right. And if you can't distinguish between the two, it gets hard for you to figure out whether or not you should be performing a particular action, like say transferring funds. Okay, so really, like, our goal is to kind of answer this question whenever we try to use one of these the defense mechanisms. So we really want to make sure that the code that we're talking to that made this request is actually our own code. So to authenticate these requests, we're going to look at three different things. We already saw same site cookies, but we're going to revisit them here and talk about their pros and cons. But there's also two other techniques, namely secret tokens, or CSRF tokens as they're called, and using the refer and origin header to validate where requests are coming from. So let's go top down. Okay, so what are CSRF tokens? Well, the idea behind CSRF tokens is we're going to rewrite anytime we send a web page to the browser, where like that may have, let's say, a form. One of the things that we're going to do is we're going to include, say, a secret token with this form. And then when the user, say, clicks the login button here and this form is submitted, this token is sent back to my web server, and I can server side check this token against whatever tokens I know I've generated or sent to the browser. Make sense? So we basically include a secret in our forms, and when we send post requests, we include these secrets back, and make sure that they actually match up with something that we've sent before. And you can do this with other kinds of requests too, but it gets a little bit tricky. The most important ones are dealing with these post requests. Now, I have a question for you. Why does this actually work? Like, why is this pretty secure? Like, how do we know that the attacker can't get at these tokens? Well, okay, so they're definitely randomly generated, so they have to be randomly generated. If they're static, you're totally hosed because the attacker can pull up their laptop and they can perform a request, from their laptop to see what that token is. So I'm going to get my own token, you're going to get your own token, and we're going to get different tokens, anytime we essentially create a session. Yeah, so the same origin policy for the DOM is the key, right? Because their attacker, they can still, like, if they ship over a page, right? So give me 2 seconds. I'm going to make a copy of one of our other slides, and then okay, I'm gonna clear this here. And let me just move it. Okay, so we're here, right? So all our forms will have the secret token. So if I, as the attacker, want to carry out a real CSRF attack, right, I'd have to, when I send over an HTML page, it will have to have a form. So form, action to whatever our login is, so on and so forth. And maybe they'll still do username, so on, password, but they'll have to include a CSRF token, right? So I have to somehow, as the attacker, guess this token. Now, one way to do it is I could send a bunch of JavaScript to essentially make a request from your browser to whatever the victim website is, and hopefully get the form element from them that has the token. But even if I perform this request, right, the same origin policy is going to stop us here and say, nope, you can't actually look at that response, right? So we could have tried to fetch the document that would contain that token, but the same origin policy doesn't let us look at it. So there's no way for us to actually guess what this token is without breaking randomness or the same origin policy. So this is kind of pretty fundamental. It's pretty great. It's like one of the fundamental assumptions that makes this thing actually work out. Okay. I guess I already had this here. Well, I guess, yeah, we went through that. So, okay, so CSRF tokens are one way to do it. Now, they get tricky because you need to make sure that you include it in every form. This can be pretty costly because that means you can't cache certain pages, in particular pages that contain forms that contain these tokens on CDNs that only let you serve static files. So you need to kind of like pay a little bit more to have your forms contain these dynamically generated tokens. You have to deal somehow with GET requests if what you need to do is authenticate GET requests. And doing that is actually a little tricky because unlike forms, when you say insert an image, right, that there's no way for you to specify here is the CSRF token that I'd like for you to send to the web server when you perform the request to fetch this image. That's not a thing. So what you have to do if you need to authenticate GET requests, that is to tell the server that you are actually, the right web app or running in the browser performing the request, you'd essentially have to turn those into JavaScript requests. So you have to use essentially JavaScript that can actually send custom requests to the server that will include this thing and then dynamically modify the page in that way. So it can get pretty gross. It's also like really error prone if you're trying to do this for a big web app. Like we found tons of bugs in WordPress because doing this is actually pretty gnarly. It also like leaks information, right? So when we talk about privacy later on, the fact that you're checking these tokens and whether or not you have these tokens, um, if a token is valid or not, might take a little bit longer for you to respond to a particular request, and the attacker might be able to time that and figure out that you visited that particular page. Okay, so a bunch of limitations, but it's pretty reasonable. The other approach is to server-side check for a particular request header, or really two headers. So the refer header contains, whenever you make a request to a server, it contains the URL of the previous page from which this request was actually made. So for example, if we're in bank.com and we click on a link to somewhere else on bank.com or make a request, the refer header will contain bank.com in it. If we're, say, at attacker.com and performing a request to bank.com, the refer header would actually say attacker.com. Now, the attacker can clear this, but that would basically leave them with this mode where you don't have a refer header. So when you make a request.com server side, you need to figure out like, okay, did this actually come from this one or did it come from this one? What should I actually do? Should I just disallow requests that don't have the right refer header? And the answer might be yes. The tricky bit though is, you also have no refer header if for the first time you create a new tab and type in bank.com, right? You're not navigating from somewhere else. It's a whole new page. The refer header will be empty. So server side, like you can't fully rely on that to give a thumbs up or a thumbs down, but it's pretty close. The origin header was meant to address a limitation of the refer header. So the refer header sends the full URL, which contains potentially sensitive information, right? So if I go to, if I have, say, a link embedded in a Google Doc, say it's a shared Google Doc between the two of us, and you click on it, and that link navigates you to my site or the attacker's site, the attacker can see the full URL, which might include the shared, giant URL that's secret between the two of us. So now the attacker learned about our shared document, right? So like URLs unfortunately have secrets in them, and the refer header would leak these secrets. Now there are policies that you can, when you serve a page, that will let you customize how much of the URL is actually sent. So you can actually strip out the full path and just send the origin. But by default, like we've done some measurements last year, and most sites send the full thing. So it's a little bit scary, and it's a kind of a big privacy concern. The other bit is at least back in, 2010 or something, when the folks that came up with the origin header did a study, they were seeing companies stripping out refer headers precisely because they would be leaking information about their internal servers or these kinds of secret URLs. So the idea of the origin header is that you only send the origin, not the full URL, and you'd actually only send it with posts because that's what we cared the most about in the CSRF world. Okay, so server side, you just look at these two headers, and based on that, you can decide whether or not you want to allow requests. But again, it's a signal; it's not a definite thing. Okay, so we have a question. How does it handle third-party applications that don't share the same origin? Right, so for certain things, like you can imagine if you're implementing, if you're implementing the server for bank.com, you don't want third-party requests, right? So if you get a request from anything other than bank.com, that's usually a pretty big red flag. Like nobody should be making requests to your web app. On the other hand, if your whole thing is replying to requests from arbitrary client-side web applications that could be run by other people, you kind of have to deal with that in different ways. Usually CSRF tokens is the way to do it. But to be completely honest, most of the time you can get away with looking at the refer header. It's actually for most web apps, it's enough, right? Like all you really care about is like, hey, is the code running in the browser mine or is it somebody else? If it's somebody else, I don't want to touch, I don't want to talk to, I don't want to handle those requests at all, right? So that's most of the time, most web apps you'll pretty much build will be following this model. For other ones, it gets trickier and you have to use CSRF tokens at the very least. Okay, so the last one is same-site cookies. So same-site cookies, like we said last time, they were meant to address CSRF attacks. And the idea is, well, hey, if the context that's sending the request is not the same site, like let's say in the strict and lax mode, well, then we're not going to include cookies. For the lax bit, we're only going to include cookies if this is a navigation link. So that means that if you send, say, a post request, we won't actually include those cookies. We'll only include them with get links. So when you click on a link, we want to make sure that that still works, but otherwise we don't. Now, this sounds pretty good, but I still mentioned tokens and the refer and origin header. And I did this even though same site lax is now the default, right? So same site seems good. So like, is this not enough? And if it's not, then if you're building a new web app, should you just say set same site to strict? Would that solve all your problems? What do you think? Okay, so you're saying yes, but you know, the user interface will probably like be kind of a pain in the ass, right? So if I click on a GitHub link, then you know, it'll navigate me to GitHub, but it will, like, at least with same site cookies, it'll look like I'm not actually logged in. That kind of sucks. With same site, it will send the right cookies, right? So okay, if your server gets compromised, all bets are off. So we're here just dealing with a case where like your server is not compromised, right? So like server side, you know, if you set the same site cookie, let's say your thing is not compromised, you're just using same site cookies, you're not using the refer or origin header or tokens. Can I as the attacker still carry out CSRF attacks? What do you think? Okay, so let's do the first one, right? So with the same site equals lax, our basic assumption is, or what we're assuming actually works out, is that, look, GET requests are not side affecting. We only need to protect post requests. So like if I click on a link, you know, that won't result to a side affecting thing. And that means there's no CSRF attack to worry about because GET requests don't do that. Well, okay, that assumes that every single web server on the planet doesn't look at a GET request and perform side effects. The reality is they do, right? So like unsubscribe links are one example of this, but you can find many others. So we basically need, even with same site lax, another mechanism to tell us if the request is coming from our own page or something else. Even if we used strict, the second assumption that same site cookies makes is that, you know, the browser will not send a cookie if this lax or strict attribute is actually set. But what if your users are using an old browser that don't support these things? What do those browsers do? Well, they ignore these cookie attributes. So those browsers will happily send cookies, which basically means that if you visit attacker.com, the attacker sending a request to the victim server will contain that victim's cookies, right? And if all you looked at was cookies again, then to you, it would look like it's coming from a browser that is using same site cookies, because you have no way of telling that it's not. And that the user actually is performing this request from your own page because you got the cookie. It doesn't look like it's coming from the attacker because the cookie's there. So does that actually make sense or not? Because I want to kind of hammer on this, because same-site cookies has gotten like so much attention. And to me, it's a total failure. It's a terrible design that we should not have done. It basically makes your life not much like easier. And in fact, it makes it slightly more complicated. So I will wait a couple of seconds for you to let me know if the attack makes sense or not. And please just speak up. You can change your name if you don't want to. Yeah, we can do it once more. Okay, let me. So I'm gonna take this diagram again. So same. Oh, let me do this. We have same site. Let's say we specified same site strict, okay? So if we're in a modern browser, what's going to happen is when we get the 200 okay, and we include the cookie, and we say same site equals strict, then later when the attacker ships a page that contains the form that performs the request to the bank. Yeah, so this is from your browser's performing this request on the running the attacker page. Then this thing won't actually, no cookies will be sent, right? Because this is attacker.com sending a request to bank.com. And when the browser looks at, hey, do I have a cookie for this? The answer is yes, we do. But the cookie says that it's a same site cookie, and the policy is that it's strict. So we won't be sending any cookies, which then basically makes the server say like, sorry, I don't know who you are. This is not a okay request, right? So this is great. This is like how we want things to actually work. The problem is, if this is an old browser, so let's say this browser is going to draw something that looks old, but I don't really know how to do that. So if this is an old browser, what I'm going to do as the browser is I don't know what this same site attribute means, so I'm going to ignore it, which basically means when I, as the attacker, perform this request, guess what gets sent? Our nice cookie. And server side, this looks like a okay cookie. So we're just going to respond back with 200. You transferred all the money. Good job. Is it to me, server side, this looks like a good authenticated request. It contains the cookie, right? And the only thing that browser should be doing is sending these cookies from, bank.com, not from attacker.com. But this is an old browser. It doesn't know how to do that. It doesn't understand same site. And, like this really only works if we get everybody that's using a browser to move to these new browsers. And that's not happening, right? Like there's a huge lag of getting people to update their browsers. And the reality is, if you're building a web app, you still have to work with old browsers. And it's especially worrisome if your security relies on these new mechanisms. So your server-side security kind of decisions rely on these new mechanisms existing in the browser, and not having a way to fall back to what do you do when the browser is actually an old browser. Okay. All right. So what should we actually do? Well, there's actually like one good idea that's coming out. It's still a little bit more verbose than I would like for it to be, but this is pretty close to something we designed. And I think it's actually doing exactly what we want, which is it's going to send, so the browser will send a header, this secfetch site header, that will basically include information about the request. Like, is it a cross-site request? Is it the same origin? Is it the same site? And this header will not be sent by old browsers. So you know server side that if you're getting this header, then it's coming from a new browser, and you can tell if it's same site, cross-site, same origin, or same site, right? So it's exactly the information you want. Like, am I talking to my own code client side? It's super duper simple, and it's taken forever to get to this point. But luckily, when you all are done graduating and building web apps, this will be a thing that you can rely on and simplify all the CSRF things that you have to do. Okay, so that's all I have on CSRF. So again, CSRF is an attack that forces the end user to execute unwanted actions on another web app where they're usually authenticated, but not always, right? Like in the case of login CSRF. So they typically target state-changing requests, not actual data theft, because the same origin prevents us from looking at these forged requests. There's different mechanisms for dealing with this. The most robust that you can use today is CSRF tokens. The problem is they're hard to implement, so usually you'd want to use it with something else for like a defense in depth approach. So you should use the refer and origin headers when you can. Same cookies is not a terrible idea, even though it doesn't do what we want. It's still pretty reasonable to use it, because at least like on modern browsers, you get some defense in depth from it. But you essentially can't do without tokens today, not in any serious way. If you were to implement these things, you should use an existing framework, because getting tokens, generating tokens, checking tokens is itself really tricky, and even frameworks honestly screw it up. So one of the things that I'd want to like suggest that you do is go look at existing token libraries and see if they screwed up, because we did this for a few of them and they screwed up. So you're likely to see a bunch more, and it's kind of fun doing this. Okay, so we look at CSRF. The next class of attacks are injection attacks. So we're going to look at command injection attacks, and these kinds of attacks are possible because we have essentially command injection bugs whenever we take user input data and somehow pass it to a program like a shell or some system that will then take this piece of data and somehow interpret it as code, right? So this happens in shells, it happens in databases, and we've kind of like seen this before, just at a different layer, right? So we've seen this with our low-level buffer overflows that basically turn data into code when this data is not properly handled. So we're kind of like re-seeing the same thing where data is turning into code, but we're going to see it at a higher abstraction level. Okay, so let's look at a very simple example, right? So like our goal as an attacker when it comes to command injection attacks is to execute, at least for this particular case, arbitrary command on the system. And again, this is possible because many times we're really bad at handling untrusted data, right? And data that is then passed to a shell is particularly tricky to handle. So like we screw this up many times, and you still see these attacks kind of pretty often, even in 2020. Okay, so we have here some C code. This C code is pretty straightforward. There is no memory safety vulnerability. We're gonna pretend there isn't one. So first thing we do is we allocate a buffer that will hold whatever is in argv1, so whatever the argument to the program when compiled is, plus 100 other bytes. And then what we do is we stir copy head n 100 with a space in between, and then we concatenate the argv and then pass this whole string to system command, right? Okay. what head does, if you haven't run head before, so this is a command that just in this case with n100 just takes the 100 lines and prints it out. Okay, so when we run this thing with normal input, like say call head with myfile.txt, at the end of the day, what system gets called with is head dash 100 with 100 and then myfile.txt, right? So this is kind of like a nice way of writing, a wrapper around head that you always get the 100 top lines. Okay, how can this go wrong? Well, we can, as the attacker, because we're not actually checking what this is, this argv1, we're just passing it to system down here by concatenating. What can we do? Well, we can insert a malicious string that contains a semicolon, right? And then contains the rest of our attacker payload, in this case, rm-rf/home, right? So like, what does this turn into? Well, it turns into a call to system that has the first command and then the second command, right? So the issue is this whole thing, this argv1 is data, but it's turned into code when we pass it to system. And in particular, it results in this command injection attack. Okay, any questions on this? So with the current PA, I think you're already starting to think about these things. But right, like one way to think of this is we should be tainting this thing because it's untrusted, and before we actually include it in something like system, we should be validating this thing. We're not going to actually want to do it this way. We're going to want to use actually better APIs. But that is one way to deal with it, is at least force me as the developer to check this value that is untrusted before I use it. Okay, so C is not special. High-level languages like have all these issues, and we use a lot of high-level languages to build server-side web apps, right? So in Python, the same program can be expressed in these 3 lines of code, where we have head dash n 100, and then we pass argv1, and again we can just pass in malicious payload that when passed to subprocess check output, it will actually execute that attacker payload, right? So the right way to handle this is to use safe APIs, right? So instead of concatenating strings the way we are in the first example, what we should do instead is use this list form, which treats everything, it essentially escapes it before it calls the underlying exec function, right? So this doesn't actually start the shell. It passes the arguments to the executable essentially as arguments into an array, right? So these are the arguments that are passed essentially as pointers to strings in the argv array that is passed when we actually do the exec ve, right? So we're going to execute head, and these are all going to be treated as they should be, which is data, not as code, right? The only thing that will get executed is this particular binary called head, right? So this will get resolved to the actual file on your file system, but everything else will be treated as data and arguments to that particular program, right? So this is like a subtle difference, but it's a huge difference, right? Like here, we're essentially concatenating strings and turning that into code. Here, we're leaving those arguments as data. So there's no way to turn that thing into code because, well, we're not going to misinterpret an argument as, the continuation of that program's binary. It doesn't really, it essentially doesn't type check at all anymore. Okay. This is not, again, anything specific to C or even Python. So this is a thing that you have to deal with in Node as well. So here I just pulled a list of code of vulnerabilities, the kind of the latest one. So if we look at the date, they're timestamped in the last month from the Sneak website. And if we just kind of scan for what they have, well, there's a command injection, another command injection, command injection, command injection. and so on and so forth. There are a bunch of CSRF and XSS too, but command injection is a big deal because people are essentially writing code like this instead of using these APIs. So when you go build real web apps, pass these things as actual data, not as strings, right? So whenever we can turn data into code, as an attacker, that's like happy times. We can totally pwn you. If you're curious about other languages, just pull up GitHub and just do some searches. For example, if you search GitHub for exec sudo $_get, which is PHP's way of putting the get request server side, well, you're going to find that that request is directly sometimes being passed to exec, in this case sudo exec. So like you have web apps that are handling requests, in this case taking device and state and passing that thing with string concatenations to sudo, and that basically means that as the attacker, just need to find this web app and send it a request with whatever I want, because I can inject whatever code I want, so I can completely take over a machine this way. Okay, so this is also like a thing that you can do, is like just do a bunch of searches and go find like what people are actually doing and see how many websites are actually vulnerable out there. Again, do not actually try to attack these websites and send bad requests. That is super duper illegal. You will probably get a huge fine, maybe even go to jail if you do this. So don't actually carry out attacks against real web apps. We're going to have that set up for you. Okay. So there's that command injection. It does appear in web apps. We typically like shell out to external programs to do useful things. Sometimes we even in scripting languages like JavaScript or Python, we sometimes even execute code within our own web app. So we use something like eval to like just dynamically execute new code. So for a while, what people used to do with JavaScript is they would take, say, the request body and parts of that body, like the pre-tax, after-tax, and whatever their auth is. And these things are strings because we're getting requests that are just basically bytes. So we want to actually turn these things into numbers. So one way to do that is you can call eval. Now, that basically means that as the attacker can just send you whatever I want as pre-tax. I don't have to send you a number, right? There's nothing stopping me from sending an arbitrary request. I just pull up my shell and do a curl with whatever I want, and totally own your Node.js web app. So what you should be doing instead is using APIs that, again, treat this data as data, right? So parse int takes a string and converts a string to an int. Eval takes a string and turns it into code. It just sometimes happens to return an int. That top result looked like a student's assignment at WSU. That's true. So this is totally crap, but you'll find real web apps that do this for real. Maybe not the pseudo, but like there are plenty of these things in the real world. And I even have one example for you a little bit later, which is a little funny or sad. We can talk about what it actually is. Okay, so we looked at command and code injection. The other popular injection attack is SQL injection. So the idea is we sometimes need to talk to external programs. We sometimes need to evaluate things within our programs. What we do pretty much in every web app is we talk to a database server where we take strings and turn them into database queries. And again, if we take strings and turn them into database queries, that's turning strings or data into code. Because that SQL server doesn't expect to do anything except turn string into code, it will happily execute anything you give it. If in the web app you didn't properly think about what to do with this particular query, you can turn benign database query into an attack. And this is what we're going to do for the next set of slides. So here, if you haven't seen SQL, that's totally okay. It's a super simple, well, it's really complicated, but at a high level, it's a very simple language that lets you perform queries like this, which basically says like, hey, give me all the rows from books where the price of the book is above 100, and then order these results by title. Right, so we can perform these kinds of where clauses that can have different kinds of logical expressions. So we can use and or not. And for our tag, the things that we care about is that dash dash is a comment, and semicolon terminates statements. So we're just going to turn simple queries into a particular tag. So we're going to do this for a form that basically has a username and password. So when you implement this thing server side, one of the things that you might do is take the login information from the post request, and then we're going to turn that thing to see like, hey, like we want to actually get that user from the database, right? So we're going to perform a select, give me the ID from the users, where the username is the login, which is the thing that we get from the HTTP request, right? Okay, so this is great. So let's actually execute this PHP code with some actual data. So first, we're going to look at what a normal input looks like. So first, we're going to make a request that has just this, just Alice set as the login in the request. So what does this look like? Well, login is equal to the string Alice, right? And then $SQL will be, select ID, where username is equal to Alice, right? Great. So this is a normal request. It's going to, if Alice is a user, give us a count that's greater than 0 when it actually executes this SQL query. And voila, we can do whatever we need to do here, like check the password, right? Okay. Now let's look at this piece of code with adversarial input. So again, we are the attacker. We can choose whatever we want. So instead of Alice, what I'll do instead is include Alice and a tick. So what's going to happen here? What is the SQL query that we're going to have? So it's going to be this, right? So select ID from users where username is equal to tick Alice tick tick. Great. So then when we get to the next line, what's going to happen? Well, we're going to actually get a syntax error because we actually have 2 ticks here, right? So SQL is going to say like, hey, this is bad SQL that you just sent me. If you get a response from a web server like this is usually pretty helpful to you as the attacker, because you suddenly like just figured out that, that data that you put in the request was handled as code. Okay, so how do we turn this into an actual attack? Well, let's, instead of sending Alice tick, we're going to send Alice tick dash dash. Right. So what does that look like? Well, the string that we send to the SQL database is select ID from users where username is equal to Alice dash, a tick dash dash tick. Okay, so what do we expect this piece of code to do? Will this type check or not? Yeah, so the rest, everything past this is commented out, so that thing will execute just fine, actually. So that's great, right? So like this thing will actually succeed because we're, again, just asking for Alice. So we know that whatever was past the dash dash doesn't actually matter. Okay. How do we go from that to a slightly more interesting attack? Well, let's remove the Alice bit and just have a tick dash dash. Right, so now login is just tick dash dash. So when we perform the query, it will have tick tick dash dash tick, right? So right now we're essentially saying like where username is the empty string here. There's no user with that username, so we're not going to succeed here. okay, cool. This is not super interesting. Now we just got our web app to crash. How do we turn this into something maybe more interesting? Well, we can make this thing always return true by just providing a tick or something truthy, which is, 1 is equal to 1, and then the rest of our comment, right? So now this actually succeeds and it finds all users. Great. So, okay, maybe like I can turn that into figuring out who all the users are or get a whole database dump. But I can also do like other kinds of damaging things, right? So one thing I can do is, as an attacker, just provide the tick to terminate that. I may actually want to do this. So that whole query just ends with no users found, but I can include another statement, another SQL statement, which is just drop table users, which will just remove everything from that particular table, right? So I could have made the first statement a true statement too, but it doesn't actually matter. I could have just ended it with a semicolon, and SQL will happily execute this because, again, it's just code. It thinks that it should be executing whatever commands that you actually give it, whatever statements, right? Like, so the SQL database, all it does is munch on strings. And what we've done is we built a bad web app that takes user input and just passes that essentially straight to the database server. The other thing that we can do is we can use we didn't comment out the semicolon, right? So the comment is pass the drop table users. In the last slide. So in this slide. So if we just look at this here, right? This whole thing is valid SQL. This is what the SQL database actually executes. This is the first statement, which selects ID. In this case, this statement will return no users. This will be the second statement. And then this is a comment. Anything following the dash dash is a comment. Does that make sense? Or maybe I'm missing something. Thumbs up or thumbs down? Okay. Let's see. So, okay, I don't think the familiarity with SQL matters too much, but it's worth kind of, you should totally come to one of our office hours because we will have an assignment that has SQL. But the basic idea is we have this tick here, which will end this blue tick here, right? So here we have one SQL statement, which just performs a lookup in the table users where the username is the empty string. So this part doesn't actually matter. The semicolon ended that statement, and we were able to add another statement which removes that particular table. Right? Like in the previous examples, we were less malicious. All we did was we ended the string, but then we provided, a where clause that would be true for everything. So this select would select everything from this particular table. Okay. The last example that I want to go through is showing you how you can use things like XP command shell, which is a thing that SQL servers have that let you spawn shells and pass, these command shell functions strings that will then be, strings to the shell. So the way we can turn our SQL injection vulnerability into a command line injection attack is we, again, terminate that string. So we're going to terminate this thing, and we just have, our top level SQL statement does nothing. It just, we just ended it here because we have to somehow end it so that the SQL database doesn't crash on us. Then the rest of the payload contains the thing that we want to actually execute, which is the second SQL statement, which is exec xp command shell. And then the string that we pass to that thing is, on a Windows machine is add the user, badass with bad password. And then the rest is just, again, a comment the way comments are written in SQL. Okay, so this lets you shell out. Okay, so that SQL and SQL injection attacks, most of the time you won't actually get to see the web server respond back the way ours did, with like errors or like messages of one user or many users, but sometimes they do. So healthcare.gov, the original disaster, actually did this, and they in fact added these SQL queries to the search results. So they had like pretty serious SQL injection attacks that were pretty responsive and not at all blind. So like US Attacker didn't have to completely guess whether or not you completed a statement correctly. They kind of leaked a lot of information. So basically, we want to keep our database choice secret for our web apps. No, never. Okay, one principle that we didn't talk about when we talked about designing secure systems, it's the Kirchhoff principle, which is basically you should not assume that your attacker doesn't know what system you have. So you should assume that they know what database system, what web server, what crypto system you're using. There's no way that they won't be able to figure that out. And if that's what you're relying on, you're totally screwed. So what should you be doing instead? What you should be doing is never, ever treating strings as code. So never build SQL commands by concatenating strings. Instead, you should use two things: parameterized or prepared statements, or ORMs. These are the two things you should use. If you ever find yourself doing this, you should cry, go take a break, come back, and stop doing that. Okay, so what are prepared statements or parameterized SQL statements? Again, they fundamentally separate code and data. So they're basically SQL queries where you leave things like the email address in this query left as question marks. So you don't actually concatenate. This is the thing that you want to fill in with user data. And what you do is then you provide your SQL engine that query. So this is code, but it's code with a hole in it. This is what the question mark is. And the way you fill in that hole is by giving it as an argument. So the SQL database now knows how to treat this thing as code and this as data, whatever this thing is. So it will never confuse whatever this user input as code. So it'll never turn this thing, no matter how it's written, how cleverly the attacker is trying to be, it won't ever treat it as code. It will always treat it as data. You can think of it as properly automatically escaping strings for you. Does that make sense? So this is how you perform, say, a select query. You can also perform a database insert, right? The way you do it is you have an insert, and again, we have the values, and then our parameters are these question marks. So these question marks are again saying, look, SQL database, here's the code to execute. I'll give you the data to fill in for these two particular values. And we're going to do that again just by having a list here with those two strings. And again, these could have been evil strings, but it doesn't matter because the server knows how to treat that as data and it'll never confuse it as code. So I think I've said separate code from data like 8 million times, but this is the fundamental thing that's happening. And if you don't deal with that, then you're all good. And if security is not a good enough reason for you, these queries are typically actually faster because the SQL server can actually cache how these queries are really executed underneath the hood. So this is called the query plan. So they're typically much faster than concatenating strings and trying to get the database engine to try to figure out how to optimize these things on demand, basically. Okay, make sense? If not, ask away. All right. The other approach that you can take is using ORMs, or object relational mappers. And so these are really nice in high-level languages because in a high-level language, you can essentially define, say, a class that represents, say, users that is then persisted to the database automatically. So you typically have these ORMs that you could just use. So in this case, we have an ORM that contains 3 different fields: the ID, name, and email. And we essentially declare what these things are. And then the way we interact with the database is the way we would with a normal object, right? So you just have, you say user.query, and then you can say like, hey, look up something with this particular email, or you can say add users, where say the user has this email address and that particular name, and then you can kind of commit. So it's essentially an object-oriented interface. And then this thing that this ORM underneath the hood converts everything here into the database query. So it performs all this. Underneath the hood, it would actually, if smart, use parameterized queries to do all the conversion to SQL for you. The other nice bit of ORMs, instead of parameterized SQL queries, is you can change the underlying database most of the time without any hassle. So you can go from SQL to NoSQL, right, to MongoDB or whatever you want, by just saying like, hey, instead of using SQL, use MongoDB. This interface remains the same. The driver underneath the hood does the mapping from this ORM to NoSQL or to SQL. So is there an attack equivalent in NoSQL? There is. This is why you should use ORMs even when you're using NoSQL databases. So these attacks are possible in things like MongoDB, and you should be using an ORM exactly for these kinds of reasons. Okay. So we've looked at injection attacks. Again, these occur because unsanitized or untrusted user input ends up as code. In general, sanitizing and filtering this input is super duper hard. We're really bad at this. We still try to do it. That's why it's still a problem. We keep screwing it up. Don't do it. You won't get it right. Just use better APIs that separate code and data, and then you don't have to think about these attacks. I can't stress this enough. You will be dealing with these things, and I urge you to like look back at these slides and do Googling of these the words that appear in these slides when you're building these web apps. Okay, so for the last last 8 minutes or so, we're going to look at cross-site scripting attacks, which are essentially injection attacks. They just happen in the browser. So cross-site scripting attacks, if we have like on the left-hand side our command or SQL injection attacks, right? The attacker's malicious code ends up running on the victim server, whether it's in a language like Python or Node, or it ends up being SQL. It doesn't really matter. The code is executing server-side. Cross-site scripting, my goal as an attacker is to run code in the victim's browser, right? So get you to like visit a particular website and run my code in your browser. To see how that may happen, let's see how a particular class of attacks called reflected XSS attacks could come out to be a thing. So suppose we're implementing Google, and one of the things that we want to do is we want to be able to take a request like this. You know, when we have google.com search / whatever, then anything that is given to us as a query string, we want to actually do a database lookup, and then reply back with a page that contains the results. So this is, let's say, just the result without any actual results. All we're doing is printing out like, hey, the results for your query, which we're just echoing back this query parameter, is the rest of this page, right? So like this is pretty normal. Like I get a request, when I reply back with HTML, I want to populate it potentially with some data for it to actually be something meaningful. So for example, when we go to google.com and then search for Apple, query string will be Apple. This request goes to the server. The server replies back with this HTML page that's sent to the browser. And right, we see here that like our query string appears in a page, right? Okay, so this is just a normal search. You can actually go take a URL from Google, mess with the path, and you'll see that you'll get reflections like this in your browser. Now things get a little bit more interesting, where maybe one thing that I want to do is create a URL that has a query string that then has essentially HTML that itself contains a script element that all it would do is print out hello world. Now, if Google wasn't good at security, one of the things that they might do is, implement their server-side code in this particular way. So it would just echo back the thing that was provided as a query. What happens? Well, when the thing is sent to the browser, it would actually send the script. What happens when I run this particular piece of code? When I visit this page, well, it would give me that alert, right? So like what happens if I give you a link to this? Well, that code would run in your browser, right? So maybe more maliciously, one thing that I can do is I can craft a URL that looks something like this, where I have a script, and that script opens a new window to the attacker.com website that includes the document.cookie in the URL, right? Well, the thing that's sent to the browser is exactly that script. If you click on the link and this is the page that's displayed to you, that thing will send your cookies to my attacker website, which is pretty sweet. I just got you to click on a link and I stole your cookies. So these are called reflected XSS attacks because the attacker script, which is part of the URL, is reflected back to the user as part of the page from the victim site. The other types of XSS attacks are called stored XSS attacks. And the idea here is I, as the attacker, store malicious code usually in the database of your web application server side. And then I get the victim to visit the page and load the code from the database into the victim's browser. So we're going to look at both of these. Before we look at stored XSS attacks, I want to mention that reflected X attacks are a thing. They are for real. It has happened against big players like PayPal, where the attacker sent phishing emails to PayPal users that contained a link that in turn contained injected code, like one of those script elements. So then when users clicked on those links, it redirected them to the actual PayPal website. The PayPal website reflected that script, right? So it started executing that script, which in turn warned the users that their account has been compromised, and then redirected the users to a phishing site where they end up, getting tricked into typing sensitive financial data. Like if the attackers were more clever, they should have had this piece of code load more code from their server and remain on the PayPal.com website. But to some degree, I guess that's good because they could have been worse. Okay. The other attack is a stored XSS attack. So where might this happen? And you're kind of seeing this all the time with things like Piazza. So I have here a photo of PHPBB. But the basic idea is when you create this kind of user content and store it server side, a bunch of times we let users, inject HTML, and then other users come visit this particular website and see that rich text being displayed with bold and so on and so forth. Now, if we didn't properly handle that user content server side, when we visit the page, it might be executing attacker code. So one of the really high-profile attacks was the Sammy worm on MySpace. So MySpace had a bunch of checks, but they kind of missed one, and he was able to inject JavaScript onto his own page, on his own MySpace page, and then he would convince people to, one of them a few to visit his page. When they visit that page, it started executing JavaScript code. Because those users were logged in, one of those things that it would do is this piece of code would post on their profile page and send a request to Sammy. So within 24 hours, this spread to millions of users because this kept actually happening. So what was going on underneath the hood is MySpace allowed users to post HTML to their pages. They were really gross things. I don't know if any of you have actually seen them. But they try to do their best. They filter out scripts, bodies, on clicks, even these links that contain JavaScript. So you can have a link that contains JavaScript. If you didn't know about this, now you know. So like clicking on a link can be really dangerous. But they did miss one, which is that you can run JavaScript and CSS tags. So in styling sheets, so one of the things you can do is you can have a style that points to a JavaScript URL. And that's what he did. So now like he had a style sheet that would execute JavaScript code and did all the things it did. If you're curious about this, I recommend looking at sammy.pl/MySpace. He's cleaned up since then. He just had a recent really interesting attack on that we will talk about during the networking lecture. But within 24 hours, it started from 70 friends to like 900,000 something, and then a little bit later, his house was raided by the Secret Service. He pled guilty, had to pay $20,000 in fine, 3 years of probation, lots of community service. Couldn't use anything but one computer, and that computer couldn't be connected to the network. So don't do these things. Again, we will have plenty of fun in the class, and there's CTFs to do this. It's not worth even for something as silly as this having to deal with huge fines and lawyers and things like that. Okay, so how do we prevent XSS attacks? Well, the simplest way is we can try to filter and sanitize whatever untrusted user data before we write it to the database or before we send it back to the user's browser. Validate all headers, cookies, query strings, so on and so forth. This is actually like really tricky to get right. When we have rich content like HTML that we want to let our users actually implement, like the best thing you can kind of try to do is have a positive security policy that says like you're actually only allowed to use like these 5 kinds of elements instead of like disallowing subsets of the HTML that you think is unsafe, because you're just going to screw that up. So we're a little bit over, but I don't think it's going to take more than 5 minutes or so. So I'm going to just keep going. For those who have to take off, please do, and you can watch from an hour 20 after. Okay, so just to convince you that filtering is really super duper hard. The reason this is the case is there's like tons of ways to call JavaScript. I'm still scared of trying to do this, and I've worked on this kind of problems for a decade or so, or maybe even more. Right, so you can have URI schemes that contain the JavaScript inline. You can have all kinds of on-event handlers, from on-submit, on-error, on-sync-restored, and there's like way more than 105. So the slide is a little bit old by now. There's CSS. There's also many different ways of encoding content. So this is, for example, one thing that you might not take into account when you're trying to make these kinds of filters, right? But like this is perfectly valid HTML, where this is how we're encoding characters. This again is JavaScript, and this broke Google's XSS filter validator. Right, so it's really tricky to get right. And just to kind of do a very simple example, let's suppose that the thing that we're trying to do is filter out all things that start with less than script, because we don't want users to upload scripts to our site. Right. So so if this is our filter, and what we do is just like remove less than scripts, what happens? Well, okay, the first thing that we're going to do is we're going to rewrite something like this into source equals whatever was in between the quotes. But as the attacker, we can be more clever. So what we can do is have less than src, less than scripted src. So what does our filter do? Well, our filter is going to remove this bit, right? And then turn that string into this string, which is script source equals whatever. That gets sent to the browser, pwned, right? And this is a very simple example, but things like this have been done to real web apps. So dealing with XSS is really, really hard. You should really try to use frameworks, but they mess it up too. And we'll talk about like different ways to actually deal with XSS. But I want to slightly point out how hard this is. And like one of my poster child is WordPress. So this is a screenshot from last year. There's a bunch of XSS, and I didn't. That isn't even the full list. And today I'm like, well, let's see what XSS vulnerabilities are, or if any, in WordPress. And this is from October 29, 2020. We have XSS, and probably a bunch more that aren't on this slide, right? So this is a real web app that's used by 25% of the web that is constantly vulnerable to these class of attacks because it's really hard to do these kinds of filtering. Instead, what we should use is CSP. So the idea of CSP is that you as the server administrator can specify the origins or domains or sites that you are okay loading scripts from when your page renders in the browser. And the idea is that the browser will only execute and load scripts from things that you've actually put on these allow lists. And if you try to accidentally or deliberately load a script that's not in this list, it won't actually execute those scripts. Okay, so I'm just going to show you a very brief overview of CSP, but we'll talk about it more next time. So here is a content security policy. So this is a header, a response header that a server would send, and this basically says like, hey, you can only load content from the same domain, which basically means no inline scripts and no scripts from any other origin. So default source is just one of many directives you can have. So for example, this header is a little bit more detailed. So it says, okay, only load from myself, from my own origin, but this is kind of our fallback. We can be more precise about certain kinds of content. So we can be precise about scripts, for example. So we can say like, we are okay with scripts coming from userscripts.example.com. Images from anywhere, and media files from media.com. So this isn't just about script, it's also about restricting where you load other kind of content from, because that stuff can either be potentially malicious as well. So things like media are things to be worried about. But also this is one way to prevent leaks if there is, for example, an attacker that happened to exploit an XSS bug. Well, if you restrict where they can actually send requests to, like where they can load images from, then maybe they can't leak that information to anywhere useful. Okay. Okay. So most of the time, what you're going to do is, if you're running your own web server, you'd include the HTTP header. If you're not running your own web server, so for example, if you're hosting your web app on GitHub, you have to use the meta HTML tag that essentially lets you include your own headers. So this is slightly less secure, but and you'll hear people complain about it, but completely honestly, it's actually much better than not using CSP. So I don't think you have to be super paranoid. So we'll go more to CSP later of kind of how we can potentially use it to prevent leaks. But on the XSS side, on the injecting code side, the thing that I want to point out is that this is still actually not enough. And the reason for it is we're not just rendering things server side. A lot of times our servers just respond to requests from JavaScript. Essentially, JavaScript asks the server to like give it data. That data is then rendered client side. Right. So we ask the server like, hey, please give me data. And then we take that data and we render it. This is how modern like single page web app fancy things, like that's what they're all doing. Which basically introduced a whole new class of XSS bugs called DOM-based XSS. So just to kind of give you like one super simple example and then call it. So if we have, say, again, our like fake search engine that would have /search !, default, whatever language, one thing this piece of code might do is have an inline script which looks at what the URL is and takes whatever is in the address bar and includes it in HTML it decides to render. In this case, it would potentially generate an option value with French as that option, and then English as the second option. So what happens? Well, again, if I somehow convince you to execute this piece of code, well, that thing is reflected in the page. If I include a script, that thing is again included in the page. If you didn't properly sanitize that thing, we're totally hosed. The way to deal with this is to actually, again, separate code from data. This is what trusted types is somewhat attempting to do. So they're basically disallowing you from using APIs like document.write and inner.html, which both take strings and turn them into code, in this case, HTML code, and say like, okay, you can't take arbitrary strings and use them as arguments to these APIs. Instead, what you have to do is you have to give them trusted types. And these are objects of a particular type. In particular, the type is trusted types. And the only way you can create these trusted type objects is with a policy template like this that basically forces you to essentially write a validator and endorse strings to be used as code. So you can think of this as the copy and verify from the RL box. It's pretty similar in that spirit where like you can't use this thing until you validate it. Okay, this is better, not great. Still got to get this right, but it is much better than anything else that we really have. Okay, so that's all I have on CSRF, injection attacks, and XSS. And next time we'll continue with more fun stuff to do client side with modern specs and things like that. Sorry for running a bit over, but I hope it was fun and maybe distracting from all the things that are happening to the world, though maybe they're all trending in a positive way. And I'll let you interpret that however you want. Thank you.